Hello, students. Good evening to all. So we are very happy to have you on today's session. I know people are like quite, like held up with your board exams. First of all, we assume that you are doing well in your board exams. Despite all your board exam pressure, and you people are like directly coming in for the revision classes. We are so happy, and we are here to like serve you for your best. So today's class, Sedu is mainly going to focus on your term one CBSE revision part. So before starting of the class, I have two small announcements. So next week and the week after, which is 13th December and 20th December, we are not going to have the regular classes. Today is going to be the last class for this term, because we will resume on 27th of December after your board exams are over. So 13th and 20th December, we will not be having your AHA Group physics classes. So you use your time and spend your time on like getting good scores in your board examinations. All the very best for your board exams. That's the first announcement. And second announcement, because you don't have like next 2 weeks classes, we are not going to give you a regular weekly task, but people are getting prepared for JE exams as well. So let us not put a halt for the JE examination. So what we will do is, we have like four basic lessons. Okay, the last four lessons, just L37, 38, 39, 40. These are mainly electrostatics and electric circuits advanced problem lessons. So anyway, term one portions are also dealing with the electrostatics and electricity. We thought that okay, we would give you an advanced lesson. If you people are quite comfortable with it, yes, you can go ahead. These are all highly JE level thing. So after you do enough revision for your CBSE board, and you think that okay, I still have like enough time for some more studies or learning part, definitely yes, you can do these four lessons. It is not going to be mandatory, like to complete on or before this deadline date, because these are all the optional lessons. So please utilize the time whenever possible, but primarily focuses on your board examinations, right? So these are the two small announcements that I would like to make. Anyway, the messages will be put up in the official WhatsApp group, right? So I don't want to consume more time from Sedu's class. So with this, I'll stop for the day. Sedu, over to you. Thank you, Sedu, and all the
Okay.
very best, guys. Do well in your board exams. Rock it.
Yeah. Thank you so much, Madhu. Hi all. Happy to meet all of you in today's session. Right. So today's session will basically be a light-hearted session, because this is going to be the session. The last session before your board exams. Right. Of course, they are going to gather up and meet for JE and NEET and for a whole bunch of other things. But nevertheless, this is going to be the last session before your board exams. Right. So I'll keep this session quite simple. And also we will have a quick look at quick revision of some concepts, right, and then we will, as we go along, we will take the class up from there. All right. And first, I would like to mention like 2 to 3 important things. One, whenever you are actually, since all of you are preparing for your board exams, right, this is going to be like an MCQ. This is an MCQ test. I hope all of you are aware of this. So please do check out your AHA Guru CBSE app. I've also made sure that I've also made sure that some more content has also been added. So I think by the time you open it now, maybe tonight or sometime around that time, so you might be able to see some more content in it as well. So please go ahead and check that. And one mock test has also been added, by the way. So a mock test paper has also been added in the app. I think the mock test is the ones that you have already attempted. So in case if some of you have failed, some of you have not attempted the mock test when it was conducted, so you can take it up in the app. So that is one regarding the AHA Guru CBSE app. Now the second thing is, when it comes to board exam, so when you actually go in, please make sure that you have a quick look at the NCRT core NCRT textbooks, and especially the summary points given in NCRT textbook, right? So I want you to go through both a quick overview of whatever is given in the NCRT textbook. Just flip through your pages so that you don't miss out anything. And second thing, right, I also want you to kind of go through the summary points at the end of each chapter, whatever is given in your NCRT. So that is number 2. And number 3, since again most of your by now most of you should have been used to writing a MCQ kind of an exam, but again I would like to mention, in case usually problems in CBSE, if it's MCQ type also, it will turn out that they're not going to be too difficult or super difficult. Most likely they will all be very easy. In case if it turns out accidentally that some question is difficult for some reason, or maybe you have not revised that, you have not read that one question, immediately don't get upset, and do not spend too much time on that particular question, because usually the underlying assumption is anyway CBSE exam I'm going to do well. So suddenly you see one question that doesn't strike you immediately, or that's something that's not familiar to you, we tend to get paranoid, right? So don't do that. Answer all the rest and come back to it whenever you find time. And also I think you've got this choice, this thing allowed, right? So I don't think that should be a problem. So these are some basic things that I wanted to let you know for the regarding the exam for CBSE. Okay. And finally, when it comes to your CBSE board exam, right, especially the day before and so on, physics is an analytical subject. You've got to work out, you've got a lot of things to calculate, evaluate, and so on. So please do take sufficient rest. Do not oversleep and do not undersleep as well. Please do take sufficient rest and go to your examination hall. Do not do that overnight study, because again, as I mentioned, it's not something that has to do with your memory. Even if it has to do with your memory, it won't function well if you're not well rested. But this is an analytical subject. You have got to calculate. If there is some fatigue in there, you cannot calculate things quickly, so that could spoil the exam temperament, right? So just take a good rest, and then like you can just go in for your examination. Avoid last minute revision, and avoid learning anything new in the last minute. Okay. So I think enough of advice. I think some of you might have heard it from several people, but I just thought I'll add it on once more. Right? Can I have my PPT added in, please? Right. So we just happened to make. I mean, I just happened to make some animations for magnetism and matter. Last class, when I did magnetism and matter, I was unable to show it. So quickly, I'll just go over this. Especially some of you had again asked this repeatedly. That you find it hard to visualize the angle of declination, dip angle, and other things, right? So I'll just play it once more. Play this animation so that it's clearer. Okay. Now observe this. So you see the earth actually spinning. By the way, this earth, the earth spinning axis should be tilted about by a certain degrees, but here we have not shown that tilt, right? I'm just taking it straight like that. And you see that because of earth's rotation, and also within the core of the earth there is some molten metal and so on, that there is some conventional current in it. Conventional current meaning, like, because of the molten metal gets churned up here and there. So because of that, and they're all mostly in the ionized form, and so you have got some tiny little currents, and all of these currents add up in such a nice beautiful way. It turns out that this constitutes a net magnetic moment. So we would like to visualize it as if a giant large bar magnet was kept inside the earth, right? And so one important thing that I wanted you to notice is actually the magnetic axis and the geographic north south. If you observe carefully, I have not kept it at the same point. Rather, this magnetic axis is tilted by about certain degrees with respect to geographical north south. And this tilt, okay, it turns out that this is roughly somewhere about like 11.34 odd degrees. So that is the tilt between the geographical north south axis and also the magnetic north south. Okay, that is the first part. And second thing, when it comes to angle of declination and dip angle and things like that, so I want you to observe this quickly. Sorry. Yeah, have a quick look at this. So here you see that I'm just showing the bar magnet, right? This is the geographic north-south, and I've shown this bar magnet to indicate the magnetic north-south. You have chosen a point. Let us say this is the red dot is a point of your interest, right? How do you find the angle of declination? So you draw a plane passing through geographic north-south and also this particular point, right? So this particular plane is going to be called as the geographic meridian, right? So this particular plane is called the geographic meridian. Okay. Now you're going to draw one more plane. By the way, that plane is going to pass through this magnetic north-south, which is that magnetic axis, and also this point, right? And you're going to call that plane a magnetic meridian, right? Observe this. You've got a point and you've drawn a plane. Now you're drawing one more plane which is passing through the point and also the magnetic axis. This is the orange plane, right? So this orange plane is nothing but your magnetic meridian. Okay, so clearly you see that this geographic meridian and magnetic meridian make some angle with respect to each other, right? This angle, if you call it to be theta, this theta is nothing but angle of declination. Okay, let me continue the video. So this angle theta is called the angle of declination. Now let's take one more point, right? Probably below the equator. And now again, you can see you have chosen this point. You draw one plane passing through this point and also passing through geographic north-south, right? Draw one more plane passing through that point and magnetic north-south. Now you clearly see that in this case, this is going to be, this yellow line is again the geographic meridian. And this is nothing but the magnetic meridian. Magnetic meridian. So geographic meridian and magnetic meridian subtend like this makes an angle. The geographic meridian makes an angle theta with respect to the magnetic meridian. So this theta is going to be called as your angle of declination. Okay. Now in the same diagram, I would also want to show one more thing. For example, look at this particular point. So this is the point of your interest, right? This is the point of your interest. Ideally, if this is the North Pole, we tend to call it, we call, right? So we call this one, this is the geographic NG, which is geographic North Pole. We would like to call it magnetic North Pole, and this one will be magnetic South Pole. We just call it magnetic North Pole, but this behaves like a South Pole of the magnet. Okay. I mean, ideally, if it behaves like a South Pole, you would be better off calling it magnetic South, right? But in general, the convention is because it's closer to the geographical North. Historically, there have been certain reasons, and therefore, this is called, the magnetic North. But if at all you imagine a bar magnet, then it looks as if the South Pole of the bar magnet is actually there at this particular point, right? And you know that if at all you have a bar magnet, right, North Pole and South Pole, you know that magnetic field lines enter the South Pole, right? And whereas magnetic field lines exit from the North Pole, because your North Pole behaves like a positive charge, and your South Pole, magnetic poles obviously, behaves like a negative charge. So North Pole, since it behaves like a positive charge, so you see that the field lines come out of the North Pole and they enter the South Pole. So at this particular point, if you were to see, right, you can see that there is going to be some magnetic field because of the Earth, right? So you can see that there is some magnetic field because of the Earth. And if you consider this line, right, to be parallel to the surface of the Earth, right, so you can see that there is a dip that it makes with respect to the horizontal, and this angle is nothing but angle of dip. Okay, so all of this I explained the last time when I did magnetism and matter, but unfortunately I didn't have this animation back then, so we happened to make it after that. So I just thought I'll show it to you once very quickly. Okay, so hopefully I think you should be able to visualize angle of declination and angle of dip, right? Angle of dip is also called angle of inclination, right? So again, don't get confused with that, because looks like declination and dip should be the same thing, but ideally it is not. Angle of declination is a separate thing. Otherwise, you have angle of inclination or dip angle. Both of this is actually the same thing. All right. And this is the first part regarding magnetism of the Earth. Okay. And it was also of interest that I just thought I would want to show this small graph, which is like main field declination, right? So what is declination? Again, the angle between geographic meridian and the magnetic meridian, right? Now, let us say you are a sailor and you want to actually sail through. So you know that the north, your magnetic compass would align in the north-south direction. Ideally, you would think that is the north direction. But now we know that because the magnetic north-south axis and geographic north-south axis is tilted by an angle of about 11 and a half, roughly about 11.3, 11.4 degrees. So if you travel along the direction your compass is actually showing it to you, you will not end up being at the North Pole. Rather, you will end up being slightly away from the North Pole, right? So, but for sailors, it's actually a big problem. So what usually sailors and, in navigation, what we do is you use a compass in case if you're using a compass. So use a compass to actually show the direction, and you know that a freely aligned bar magnet or this particular compass in this case would align parallel to the magnetic north south. So that idea is clear. It aligns parallel to magnetic north south, and you know the angle that the magnetic north south makes with this geographic meridian, right? If you keep on measuring that angle, and that angle is angle of declination. So people have actually mapped that angle, right, across this globe. So you can see like different lines, right? So for example, if you take this line, right, along this complete line, the main field declination is about minus 20 degrees. So as long as you keep moving along this line, so you need not keep monitoring. You need not say that, okay, my compass shows a certain reading, I have to shift by declination, right? But this declination is constant. So you know that the calibration that you have to do is actually constant. You know that 30 degrees left or right, you'll have to shift based on the main field declination. But when you want to move from one line to the other here, for example, when you want to move from this line, which says declination minus 20, to this line declination minus 30, that means there is a change in declination itself, right? So you need to recalibrate your measurements once again. All right, so this is one interesting way, because why should someone be interested in measuring the angle between geographic meridian and magnetic meridian until there is something that's until it's absolutely necessary for some reason or the other, right? So people have actually measured it and they have mapped it, and this map you can also find it online if you just Google main field declination. Okay, so I hope this part is also clear. And before we go on to a bunch of current electricity and other things, I remember like last class I said, magnetism class, I said I'll solve this problem, but unfortunately towards the end time was up and I was unable to clarify this. Actually, it turns out that there is no trouble in this problem. This problem is perfectly legitimate. Some of you might have tried, but have a quick try and let me know in the comments. So it's not quiz one. Maybe just call it solved example one, or no, or exercise one, solve exercise one. Okay, quickly solve it and let me know the answer. I'll give 2 minutes. Okay, meanwhile, while you guys solve, I've got a bunch of questions. Harsha Rajkumar, CBSE is setting very lengthy papers. Yes, I do agree with you on that. At times, CBSE paper is really lengthy. Can you give us tips on how to manage time? Right. So, I'm not inventing a new strategy here, but it's the age-old strategy. So, when you actually solve a question, right, and by the way, this is all MCQ. At least you do not have to write it and present it and all of that. At least you're saving a bunch of time there. And second thing, if you find that some problem is lengthy, you can always return back to it. See, I'll tell you the problem. You're given about 20, 30 questions, and it turns out that the second question or third question is extremely lengthy. Right? Many a times you will be able to understand looking at the question whether the question will be lengthy or not. For example, after this, I'll give you one or two problems in current electricity, just as a quick revision or a recap of the concept, very basic stuff. You'll be able to see immediately that this question is really, something that's very simple, no complicated calculations involved. So first, solve such questions, get some basic marks, keep it safe. Then when it comes to, questions that are actually calculation intensive, questions that are very lengthy, you solve it, number one. Number two, also please look at it, look at the options. Sometimes options you could, there is a possibility that you could eliminate certain things in the options. It might also happen, right? Before you kind of attempt to do a very lengthy calculation and you decide you're going to apply brute force and calculate it, do an extremely lengthy calculation. Before that, spend some time, look at the option and first ask yourself whether these options are making sense. Is there something that you can directly eliminate? Right? Because many a times what happens is CBSE so far has been a descriptive paper. Now suddenly it's becoming objective, right? So don't solve it in the age-old style where you'll say, I'll read only the question, I'll solve whatever answer I get. If it's there in the option, I'll tick, right? When you read the question, have a quick look at the options as well, right? And sometimes you might also be able to apply dimensional analysis. Again, a word of caution, if you are trying to apply dimensional analysis and you find out that there could be certain constants that are dimensionless, you are in trouble, right? So make sure that the constants involved are dimensionless, or if they have the dimension, just check that out properly. If you're doing dimensional analysis, well and good. That is one more way in which you can save time. So just check that out. Okay, that is one more thing. And the other tip is whenever it comes to large calculations, right? For example, in the options, if at all the numbers are 10 power minus 4, 10 power minus 6, 10 power minus 8, and 10 power 3 or something like that. So clearly you see that whatever number before that would not matter pretty much, right? You can get away easily with an order calculation, right? You need not calculate the exact stuff. You'll be pretty much okay if you kind of calculate it with respect to the order, right? In what order is it, then that should be quite okay, right? So these are some of the things. As we go along, I'll also tell you some other quick tips. Okay, Atharva Desai, why is this magnetic effect caused? Why is there a magnetic field attributed to the Earth? There is still some kind of we have not settled that. That's not a problem. That's completely settled. The basic understanding is because just imagine you have molten metal, right? And then molten metal, it's all like going here and there, and then you know that at this particular very hot temperature, right? So some, if the metal is also ionized, it's a positively charged metallic ion plus a sea of electrons and things like that, right? When that flows, right, flows as in, because it's a liquid, so when it just flows, right, so you see that giant currents can be set up, right? So you can have tiny little currents, and they can all add up to give certain magnetic moments. That is something that we believe to be true so far, right? But still there is a lot of research going on, so it's very hard to say like exactly it is because of what. But so far, with the understanding that we have, this is the answer, right? And by the way, it is not this geographic, there is a flipping of this magnetic axis as well. It happens, it has, compared to the age of the Earth, it has happened quite a bit of times, right? It's not as if it's always inclined at an angle, at 11.3 or 11.4. Sometimes there is a flip of magnetic north and south as well. It happens once a while. Okay. So, all right. So let's quickly go back and okay, hopefully all of you have responded. Right. So I see many of you have responded, and majority of you have said it is option B. Okay. I doubt it is option B. I don't think it's option B at all. I don't remember. Anyways, let us just solve. Right. So this problem, let me quickly solve. So it says a bar magnet of length L and magnetic dipole moment M is bent in the form of an arc as shown in the figure, right? So you've got an arc. Okay, this bar magnet of length L. So just consider this length to be L. Of course, there is a slight assumption involved here that, it's a bar magnet of length L. You take a bar magnet of length L and bend it. There could be some stretching, some additional length and so on. Just ignore that. Just think that this length is actually L. Okay, this length is L, excuse me. That's okay. Yeah. So this length is L, and let's just say this subtends an angle how much? This subtends an angle of about 60 degrees here. Okay. And then its magnetic dipole moment is capital M, right? The new magnetic dipole moment will be how much? Now you know that this is one pole, magnetic pole, and this is one more magnetic pole. What is the whole magnetic dipole moment? Pole strength into length between the two. Right, between the two magnetic poles. So in the old, the actual bar magnet which is not bent, this length is L, right? And you've got two poles of pole strengths, let's say M and M, right? So what will be the magnetic moment? Magnetic moment will be nothing but M times of L. This is going to be your magnetic moment. Okay. Now here you're supposed to calculate your magnetic moment. Okay. So the distance between these two magnetic poles, right? This is something that you need when you calculate magnetic moment. Okay. Now for that, just drop a perpendicular. If this angle is 60 degrees, right? So clearly this angle is going to be 30 degrees. Okay. If this angle is 30 degrees and this length is given to be R, right? So what will this side be? This side will be R sine theta. This one will be R cos theta, right? Which is nothing but theta is equal to 30 degrees. So similarly, here also it is 30 degrees. This length is r. So therefore, this will be r sine theta. Okay, so the total distance between both of these magnetic poles is nothing but 2r sine theta. And clearly, you know that sine theta is equal to 30 degrees. So therefore, you know that 2r into 1 by 2, which is equal to r. So the new distance between the two magnetic poles is actually r. Okay, but you know a relation between r and l using l equals to r theta, right? So l equals to r into theta, which is actually 60 degrees. But whenever you use l is equal to r theta, remember this theta has to be in radian. By the way, I'm stressing on this point because current electricity also sometimes you might be given some wires bent and certain things you might have to calculate it. So whenever you use l equals to r theta, remember this theta is in radian, right? So l equal to r into, and this is going to be nothing but pi by 3, right? Pi by 3. And so you've got r is equal to 3l by pi. Okay, now what will be the total magnetic moment because of this? So it is going to be 3l by pi into, this is nothing but the length between the two magnetic poles, right, into magnetic moment, into the pole strength, which is nothing but m. But you know that magnetic pole strength into this l was actually equal to the old magnetic moment ml, this old magnetic moment capital M, right? So you can say this 3 into lm divided by pi, and this l into m was the old magnetic moment, which is nothing but 3 capital M by pi. Okay, so the right answer is option A. This has come in neat, right? So last class, I just thought there was some problem with the question, but actually it turns out that there's no problem with this question, right? So quite a bit of chance that such questions might turn up. So have a quick look at it. Okay. Uddhav, Hemant. So this is regarding magnetic moments. So magnetism and matter part, like just the first part of it, right? When you read through, you might find this. So magnetic dipole moment or magnetic moment is nothing but pole strength into distance between the poles. Exactly analogous to electric dipole moment, right? Take a quick look at it, and then we will solve 2 or 3 very simple problems in current electricity. So I'll give, but by the way, these current electricity problems, ideally it should not take more than 1 to, if you can do it like in 30 seconds, 40 seconds, it's okay. If not, it should not take more than, let's say, a minute or minute and a half, right? So let me give you, because most of you have responded B, just check out in case if there is some calculation or something, do let me know in the chat. I'll give you 1 minute, then we can go ahead and solve next problems. Okay, let's move on further. Try to solve this problem. So let's call this exercise or example, maybe you can just call it 2, right? By the way, this is also a previous year CBSE kind of a question. So there is one resistor. Let us just say, I'll give the resistances at last. And you've got one more like this. Okay, so this is A, this is B, this is C, this is D, right? And all of these resistances are R. Very simple one. Calculate effective resistance about AD. This is example 2, very simple. Some of you should be able to do it like mentally as well, right? And one more example, again quite simple, but just think about this. You've got one more circuit like this, right? So mm, you can solve example 2. Please send separate question pop-up boxes for both of this. Let me solve this one meanwhile while I draw this. Right, let me quickly check this out. I think there's one more resistor, right? Two. Yeah, there are three resistors. Three and then two. Just a second. So I happen to see it. Okay, let us just say that a battery of EMF E is connected, right? And then all of these resistances are R each. Okay, calculate the current which is flowing through. Let us just say calculate this current which is flowing through. Maybe I call this A, B, C. Right? Calculate this current that is flowing through this arm, which is like A, B, C. Calculate this. The question might look a little strange for some of you, but just calculate both of this. Two simple problems. First one I'm not going to solve. I'm just going to quickly go over this, but come on, quick. I mean, why are some of you not? Why are you some? Why do some of you think it? You're not sure with the answer for the first one. Solve example 2. What is hard and solve example 2? Yeah, try equivalent resistance about AD. Come on, make it fast and also solve example 3. Please send one more poll. Solve example 3. I thought you guys should not have a problem with this. Some of you are done with this. Also solve one more question. Solve. This is going to be example 4. Okay, so let us just say you have 2 amperes going in and 2 ohms, and you've got a 3-volt battery, and also you've got 1 ohm, right? So let us just call this point A, let us call this point B. Just calculate what is VAB. By the way, this has come in NEET 2016. Very simple, but hopefully I don't think people will make mistakes in the science, right? Anyways, so let us just solve the first problem. First problem, please do not make a mistake, right? See, you're asked the equivalent or the effective resistance about AD, right? So that means what? You're measuring everything across A and D, right? Let's just say you put one battery kind of a thing, so everything will happen across A and D. Then remember what will happen. This part of this resistor has nothing to do here. This resistor also has nothing to do here. It doesn't contribute to any effective resistance at all, right? So effectively you're left with this branch. So both of them are in series. So I can take both of them and I can write it, because they are in series, it will become 2R. And this one, they will be in series. So this will become 2R, right? So 2R and 2R, they are in parallel. So effectively it becomes R, right? Effectively it becomes R. So you delete everything and just write only R here. So you've got 1R, 1 more R, 1 more R, 3 R's in series. So the actual resistance is 3R. By the way, I see variety of answers, but please be careful about such things. Whenever you're asked effective resistance about AB or AD, I mean, here clearly you can see that this resistor doesn't matter. This resistor doesn't matter. What you could have, like any 100 ohms, 1000 ohms, anything you could have, but here it doesn't matter, right? So the right answer is 3R. This was, I think, 96. It has come in CBSE, and probably it has come in APMT, I believe. And the value of R was given back then to be 10 ohms. So then if at all R equal to 10 ohms, overall will be 30, right? So come on, try out solved example 3 and solved example 4. No, Sriram Srinivasan, I think that was the problem. Take the distance between the poles. I repeat, just take the distance between the poles, right? I remember, I didn't exactly remember why there was some problem in the question. Just take the distance between the poles. However, what do you do for a electric dipole, right? So you have two charges separated by some distance. Whatever is the distance between two charges, you take them, and then like magnitude of the charge into distance between them, right? So that's how you calculate magnitude of electric dipole moment. So similarly here also, just take the distance between the two charges, right? The one that we have done today is correct, so please stick to that. Yes, Anantaragavan, that's a wonderful this thing to discuss, but it requires a little bit of uh, length contraction and things like that. The Lorentz, it requires a bit of Lorentz transformations, but nevertheless, I'll give you a very rough intuition for it as we go along. Right, I'll do that. But probably, if not in today's class, we will do it in. We will explore it quite a bit in. The subsequent classes, especially when we do some JE revision. Also, I would do that. Okay, but still, if you are extremely curious and if you would like to read, I would. I can probably send you reading material to actually read that. Right. So it turns out, but in nature, that there is only one thing called an electromagnetic field, right? And it depends on, like, for example, it really actually depends on which frame you are, so as to feel either electric field or magnetic field. See, I'll give you one simple intuition as to why it should happen like that. For example, a moving charge, right? A moving charge or a steady current constitutes a magnetic field, right? That is something that's known, and you have done Biot-Savart's law and a whole bunch of other things. Now, let's say there is a steady current of about 2 amperes or 3 amperes established in a circuit, and there is a steady current. It's just continuously moving up. Let us just say, right? See, if some of you are wondering what we are discussing, Anantaragavan has just pointed out that in Professor H.C. Verma's book, it's given that magnetic field and electric fields, they're actually one and the same, but one is the relativistic effect of the other. So I'm just trying to quickly give him an intuition. Meanwhile, others can solve this. In a minute, I'll just come back and solve. Okay, look at this. Right, so let us just say you have a wire in which there is current, right? So let's just say it's nothing but like flow of charges, right? So it could be, ideally it's electrons, and the opposite. So if electrons move like this is the direction of conventional current. Now let us just say, in a frame of reference, let us just say you also like move with the same velocity that the electrons have. So you also move with the same velocity, you move parallel to these electrons. So now with respect to you, what do you say? With respect to you say that no charges are moving, right? So no current, no charges in motion, because you and the charge, they have the same velocity, right? So you see, with respect to you, there is nothing that's moving. So now you will be in a tendency to come back and comment and say, look, I don't see any, I should not be seeing any magnetic field. Whereas someone on the ground, right, some ground observer is actually going to say that no, there is some magnetic field, right? Because with respect to a ground observer, there is a flow of charges, there is a steady current, and there is a magnetic field. Now you see, both of them have some contradictory responses. So one guy is saying there should not be any magnetic field, the other guy says there should be magnetic field. Now what turns out is that if you observe a physical phenomena, right, if you make predictions about certain physical phenomena in both the frames independently, you will see that the physical outcome is the same, right? So the whole idea in it is like, it is one field. If you treat it as one field, which is an electromagnetic field, it will turn out to be very convenient. You'll just see in different frames. For example, for different people, it manifests in a different way. See, for example, I might see that I might call it to be an electrostatic force, you might call it to be a magnetic force, rather, depending upon which frame of reference you are in. But the effect produced by the both, and any physical consequence, that should be similar, and that both of us should agree upon, right? Just think about it for a little while. We will do a detailed this thing sometime later. By the way, I think it's quite a bit of time. Solved example 3. Any answers? So yeah, Dhruv Krishna, but you can also visualize that you are also moving at such high speeds, like, along parallel to the electrons, right? So I mean, you need not move like that, but at least you can imagine and you can think that with whatever the velocity electrons are moving, if at all, if not you, if someone were to observe in that frame of reference, certainly things would turn out to be different, right? So anyways, so second question, let's just see how many of you have given the right answer. Again, I've got varied answers. Okay, glad that I asked this question. Okay, I'll read out the answers, by the way. Some of you have got E by 2R, some of you have got E by R, some of you have got 5R, 5R by, 6 by 5R, some of you have got 5 by 6R. Variety of answers. Let's just go through this. Right, let me delete the other part and go through this quickly. By the way, this is also previous year NEET question. Okay, now you've got a circuit like this. First, let me just detach the battery, right? Ideally, in the question, it was given like this, and it was told that a battery of EMF is connected. So it's easier to look at the circuit like this, right? Now, first thing that you need to do is just try to open it up like this, right? So imagine that there is, it's like a wire mesh. You hold A, you pinch at A, and then you open up the circuit. Let me redraw that circuit here for you, so it becomes easier to see, right? This is B, and here you had A, right? So I'm just flipping it up open like this, right? So maybe I would want to show it to the paper. So I've got a plain sheet with me. Okay, just a second. Right, so you've got some circuit like a triangle, right? Now let us just say you open up this A, right? You flip open this A. So what do you get? You clearly, when you flip open this A, this branch and this branch goes to the other side. So you can clearly see that you can redraw it as, so you've got one resistor and one more resistor, right? And this point is nothing but A. So let me draw A here. This point is nothing but A. You've got, I've just drawn the same A thing here. And again, you've got, this is B. From B, you have got a resistor till C. From B, you've got a resistor till C, right? And then from C, right, you're connecting, let us call this point maybe some D or something. Okay, this is this point D. And between these two, you've got one more resistor. So it is like this. Okay. Now, what did I ask you? I asked you the current flowing through A, B, C, this branch. So the current flowing through A, B, C, D. I asked you the current flowing through this branch A, B, C, D. Right. Now, this circuit again, let me redraw it properly so that you can recognize it visually. Right. So it's clearly a Wheatstone bridge, just that people have drawn it in a lot more messier way. But clearly you can see that this is a Wheatstone bridge. Right, all of these resistances I gave it to be R everywhere. So clearly this is a Wheatstone bridge. Wheatstone bridge is also balanced, right? The ratios turn out to be such a way that the Wheatstone bridge is clearly balanced. So in that sense, what do? Just take off this resistor, pull this resistor out, right? If you pull out this resistor and if you again label these points, you've got A here, you've got B here, you've got C here, and so on. I clearly asked you what is the current through A, B, C, this part, right? This current, what is the current through this? Okay, assume that a battery of EMF, I said E is actually connected. Battery of EMF E is connected. Then what would happen? So clearly you see that this R and R are in series. So effectively you're left with 2R, right? So you are left with 2R because of this R and R. And because of this R and R, you are again left with 2R. So let me draw that as well. Because of this R and R, you are left with 2R. And clearly you see that both of them are in parallel. Again, if you simplify it further, you know that 2R parallel gives rise to R in series. Right? So you've got R in series. Now you can estimate what will be the total current. The total current will be how much? Total current will be E by R. But this is not the answer to the question, remember, because you have been asked to calculate the current through this branch, that is A, B, C, D. This is this current that is flowing through this branch that you're interested in. So again, if you just decompose it back, right? So what did you have? You had like total current, you found out that is nothing but epsilon upon R. So you saw that there was one branch of the circuit like this, right? So you got one branch of the circuit, one more branch of the circuit, one more branch, and one more branch, right? So if E by R flows through this way, you clearly see that the circuit's all symmetric, right? So here also on the uppermost branch, you've got 2R resistance, lowermost branch also you've got 2R resistance. So therefore, whatever current goes in, it has to split. It has to exactly divide into half. So current through this branch will be epsilon upon 2R. Current through this branch will also be epsilon upon 2R. Right? So the right answer to this question, the current through A, B, C, D, that is actually nothing but epsilon upon 2R. Right? So the right answer is epsilon upon 2R. Okay. So this is again a Wheatstone bridge construction. Obviously, when it comes to Wheatstone bridge, it could be asked in a slightly different way as well. So just be a little careful. I just wanted to give this one problem to kind of check whether this Wheatstone bridge idea is actually clearer. Any doubts? Hopefully this circuit should have also been clear. Shri Vasant, I'll let you know. I'll let you know what is a study plan. I'll give you I'll give it to you a bit towards the end. Okay. People who have made mistakes, are you clear? Like where you have made a mistake, and probably I think you should concentrate a bit more on this so that you don't make mistakes like this in the exam. Right. So let me clear this part and quickly go on to solving this bit. So this is again a very simple one, this NEET 2016 question, but I have put it deliberately here so that all of the sign convention and other things, it will give me an opportunity to go through. Right. So let me quickly go over that. Okay, so this question, how do you kind of solve? So let me redraw the circuit. So you've got A, you've got 2 ohms, and then you've got a 3-volt battery, and then you've got 1 ohm resistor, and then you've got B. By the way, questions like this, I've given enough number of questions like this in the consolidated test. So I don't think you guys should be making a mistake in such kind of questions, but you're asked potential drop from A to B, right? So what do you do in order to calculate the potential drop from A to B? You can calculate potential drop because of all of these individual elements, add them up so that you can find out the overall potential drop, right? When it comes to a resistor, remember potential drop in the direction of current, right? It is nothing but IR. Okay, this is the direction of current. This is my potential drop in the direction of current. This is nothing but IR. So that is how much? 2 into 2, which is nothing but 4 volt. Okay, now potential drop here, this is positive terminal of the battery to negative terminal of the battery. So therefore, indeed, there is a drop in potential. So the potential drop will be nothing but 3 volt. Okay, and similarly, when it comes to here, so you can clearly see that this is potential drop again in the direction of current. So you can say that it is nothing but IR. So you have got I into, which is nothing but 2 into 1 ohm, which is nothing but 2 volt, right? So this is also equal to 2 volt potential drop. What is the overall potential drop? Potential drop because of this plus potential drop because of this plus potential drop because of this. So it is 4 volt plus 3 volt plus 2 volt, right? So which is nothing but 9 volt is the potential drop. Okay, so this 9 volt is actually the potential drop. Right? Any doubts in this question? Exactly, Abhishek, but the current through the battery is E by R, but that is not asked. Right? You're asked the current through the branch. Right? You're asked the current through that particular branch. So that is what you're asked in the question. But exactly, if it is current through the battery, then it is E by R. Correct. So some of you, I mean, since I have read that question, if some of you had thought it is current through the battery and evaluated it to be E by R, that should be okay. But otherwise, the current through this particular part is not E by R, it is actually E by 2R. Okay, ideally this thing should have been like this, right? So you've got one resistor, you've got one more resistor, you've got one more resistor, right? You've got one resistor like this, one resistor like this. Okay, so now the current should have been through, let us just say A, B, C, the current through A, B, C. Current through ABC was the actual question. Current through ABC is nothing but epsilon upon 2R. But if it is current through, if at all you had D also here, if I asked you what is the current through ABCD, right, then clearly ABC current is different. If you kind of split it and see, it will be different. Because of one branch, there is epsilon by 2R. Because of one more branch, there is epsilon by 2R. So put together, whatever is the current through the battery, that is nothing but epsilon upon R, right? So there is no trouble in it. Hopefully it's all clear, and this problem is also clear. Remember, when it comes to a resistor, it is the potential drop along the direction of current. Okay, so revise Wheatstone bridge when it comes to current electricity. Right, specifically revise power part. I mean, like I square R, like the joule heating this thing, and also revise Wheatstone bridge. Series parallel, anyways, you already know, right? And some simple questions like this could pop up, right? And if you have time, just go through, in case if you guys have time after solving all of this MCQ questions and other things, whatever is being given in your school, if you have time, please go through the old NEET questions, like the the AAPMT questions and things like that. Go through the very old NEET questions. They will be relatively simpler, but quite a bit of chances that because it's the NTA, right? So there's quite a bit of chances some similar questions pop up, right? Revise these both, and also that drift velocity is NEAVD, that part also, the drift velocity part, revise it once more. Okay, current electricity, Wheatstone bridge, and series parallel simplification. And if at all resistance is given, like suppose material, it's there is a long copper wire, you melt that copper wire and then you rewind it to something else, and what will be the total resistance and things like that. Such kind of problems also, please focus on it. Okay, any doubt so far? Right, someone had asked, can I just explain how do I open up the circuit? Very simple, just think that you're holding this point, and just you're turning the circuit like this. So this point I'm just drawing it here, right? And this A and B, I'm just connecting it like this. This part of the circuit, it has gone here. This part of the circuit, it has gone here, right? So it is just equivalent to opening it up. It's like flipping up this sheet of paper, right? So imagine that this corner was A, right, and this corner was B. It is just like opening this paper. It's like flipping the sheet of paper, right? I hope this should have been good. Okay, I'll give you a quick 1 or 2 more minutes to quickly recollect and recapitulate everything, right? I'll give one or two more problems in current electricity, then we can go on to AC part. Okay, take a quick 1 minute to recapitulate. I'll give you one question meanwhile, right? So let me look for some nice circuit question. Yeah, I think pretty much like in the need part, I found these two circuits to be relatively challenging. That's why I had actually given it. If it is okay, then maybe we can even move further. So we can move on to alternating current. Okay, now let us look at alternating current. Right now, what is alternating current? See, if at all you see that so far in all the circuits that we have seen, right? So what have you seen? That there is a steady current. Steady current means what? So you have seen that, let's say you take a battery like this and then you connect it to and this battery is being connected to a resistor of resistance, let's say R. So you know that some steady current in this circuit will be established. And if you observe, if you were to draw a graph of current versus time, right? Let's just say that this is 2 ohms and this is 4 volts, right? So this current will be V by R, right, which is 4 by 2, nothing but 2 amperes. So if you were to draw the current versus time graph for this, so clearly you would be able to see that this will remain like this, 2 amperes forever, right? Forever, as long as this battery doesn't wear out. So you will clearly see that this is going to be 2 amperes, right? But alternating current is one where you see that this current, right, it need not be a constant. It need not be a constant with respect to time. Rather, it can vary with respect to time, right? One example could be, let us just say you have a curve like this. Okay, let us just say you have a curve like this, and if it is time and this is current, so this is a current versus time kind of a graph. So you clearly see that current raises up to a certain value. Maybe you can call this T by 4, you can call this T by 2, and you can call this T, right? So in one complete time period, what happens is current starts from 0, reaches up a peak value, and then you see that current drops, again reaches a negative value, negative peak value, again it goes to 0, right? So you clearly see that current is actually alternating. So such kind of currents are called alternating currents. By the way, when it comes to alternating currents, it need not be the case that always this waveform should be symmetric. For example, sometimes I could have a very large peak here and a very tiny little peak there, right? So that will also be considered as alternating current, and all of this, analysis, the analysis will be common to whatever kind of this thing you do, right? So this is a basic example for an alternating current. Now, some of you might wonder, now, why is this alternating current, this thing so important, right? See, in fact, this debate of whether we should have for power transmission, whether you should have direct current or alternating current, it was a big battle in history. Right, so several prominent scientists were involved. A whole bunch of people said, they thought alternating current was better to be used, and a whole bunch of people said, no, it has to be DC, right? But finally, at least now, most of the countries, so that we use alternating current for large distance propagation. Whenever where you need to send current through very large distances, right? So for in your electricity grids and things like that, we use alternating current. In fact, like the one that you have in your like the power supply that you get to your home, right? So that's also an alternating current. Okay. Now, alternating current, anyway, understood. Now, how about generating an alternating voltage, right? Because you have a current, it's very hard to understand if I don't tell you how to think about generating an alternating EMF. For example, if at all you had an alternating EMF which varied, sinusoidally, which varied in a different way, then you can see that if at all the potential was varying sinusoidally, it's easier to establish that the current should also vary sinusoidally, right? But in a moment, we will see from basic ideas of electromagnetic induction, how is that you can achieve something like a varying EMF. Instead of, for example, this battery gives you a constant EMF as long as it is healthy and functioning, right? But whereas now we are trying to look at sources which will give you a varying EMF, as in the EMF itself changes both magnitude and polarity. So we will look at certain examples of things like that. That is number one. Meanwhile, I've got one more interesting question to ask in current electricity, but please send this as a question pop-up, not as a poll, right? I want to look at the explanation of people as well in this problem. Okay. Let us just say you have a geyser, right? Wherein, imagine the age-old geyser, wherein if there is a resistor, right, and you send some current through this resistor, right? You connect it to a power supply, you can send some current through this resistor, and this is your geyser. Okay, because of some joule heating, you see that this resistor heats up, and here it's all water filled in. So it transfers, the resistor's heat is actually taken by the water, taken by water molecules in there, and they actually heat up. Right, so this is what happens in general, right, when you have a joule heating. Now I have one small question to ask you. Suppose, let us just say 5 amperes of current went in. Okay, and initially everything was turned off, the water was at room temperature. Now 5 amperes of current goes in, and this water is getting heated. That means how many amperes of current should come out? So is it equal to 5 amperes, or do you think some current is going to be consumed and it is going to be, let us say, 3 amperes or 2 amperes will come out, because the remaining whatever amperes was there, it will be used up in actually heating the water, right? Do you understand the question? So you've got a geyser heating up water, right? So you send 5 amperes in. I'm just trying to ask you, will all the 5 amperes come out, or only 3 amperes will come and remaining 2 amperes, and remaining 2 ampere goes into heating up water molecules? Okay, answer that. Number two, if some of you think it's 5 ampere that goes in, it's 5 ampere that comes out, I want you to also answer, then why is the water getting heated up? Right, whatever has gone in has come out, right? Now, where is that excess energy coming for water, and why is it getting heated up? I want you to think about this question, give your detailed explanation in the chat. I'll be happy if something like that turns up in your board exam, but I don't know if it'll turn up or not. But this is a good thing to understand. Just respond to me after this. uh, I'll go further and proceed with alternating current. Come on, quick. Samyukta, don't worry about the test, right? So, yeah, please respond. I'll give you 2 minutes, or take even 3 minutes to think about this, but think and answer. Okay, I've received only like 10 responses so far. But I'm happy that the response is correct. So I'll give you 2 more minutes. Quickly think and answer what should be this thing. I mean, this is a question that one student had asked me. So I thought, but it's a good question for discussion. So I just thought we should discuss it. Others respond. Okay. So I think some of you are still thinking. Let me give the answer to this question. The right answer is current does not get consumed up, because though we say, like, current bill, though we also say that this fan is taking up a lot of current, this geyser is consuming a lot of current. It is not consumption of current. Right now, whatever 5 amperes goes in, as most of you have, in fact, rightly pointed out, it is the same 5 ampere that will come out. But now, where does this water get that extra energy? It is not extra energy at all. In fact, if you observe, if this is at a potential 0 volt, and if this is the EMF of the battery, this will be at a potential E, right? So now charges, and everywhere all of this is in E, right? Same potential, and here everywhere it is all in 0 volt, right? So one end of the resistor is maintained at potential E, and the other end is maintained at potential 0. Now what happens whenever charges enter here? So let us say 10 electrons enter here. Okay, 10 electrons, with what energy do they enter? Let's just say 10 into whatever is the potential at this point, E, right? So with this much is the potential energy acquired by the electron. So electrons enter with such potential energies. When they come out, same 10 number of electrons come out, right? But what is the potential energy here? Into potential, 10 into 0, this is the potential, right? So 0 is actually the potential energy. So what has happened? It has lost all of its energy, because which kind of energy set up by this electric field? Who sets up that electric field? It is a battery that sets up this electric field. So clearly you see that there is a loss of energy, and that is that loss of energy that gets converted into heat energy. Okay, in fact, if you need to understand it even better, let us just say I take a phone, right, any object, and I drop my phone, right? It hits the ground. Now what happens? It had some potential energy, right? On it, when it just hits the ground, its potential energy becomes 0, but I retrieve my phone, right? So phone with higher energy. Now this is a phone with lower energy. Whatever was this, energy, that this potential energy that was lost in transit, that was converted into kinetic energy of the phone. Here, similarly, electrons came in with a lot more electrical energy, right? And they come out with less electrical energy. Whatever is the differences in energy, that energy is used up, and that is used to heat up water inside the geyser, right? So don't think it is the current that is being consumed. I mean, ideally it is not charges that are not being eaten up or something like that. It's actually the energy. Charges lose certain amount of energy. It is the energy lost by the charge that is actually going into heating up water. Okay, so this is one more interesting question that I thought I might want to share. Anyways, so let's go on to alternating current. Right? In alternating current, again, I said first we have to discuss, right? So before we discuss average and root mean square velocity, I'll show you one way of generating an alternating EMF. Right? So now let us just say you have a north south, you have a magnet, north pole of a magnet, you have got a south pole of a magnet. Just imagine I'm just showing you a top view kind of a this thing. So you see that electric field lines go from north pole to south pole like this. Okay, now let us just say you take a loop, a metallic frame, right? Okay, and let us just say you rotate that metallic frame. Let's say you do it mechanically, you connect it to an axle here, and then you rotate that frame mechanically. Now what would happen? So you clearly know that magnetic flux through this plane changes, and if there is a change in magnetic flux, there has to be an induced EMF, right? If there is a change in magnetic flux, there has to be an induced EMF. Now, let us just say you rotate it with a constant speed, let's call it to be omega. You rotate it at a constant angular velocity, right? With omega, then what do you think will be the actual, flux, right? Magnetic flux. So you know that magnetic flux is nothing but, so it's exactly like how you calculate electric flux, but here you see that the magnetic field is constant, so everything can come out of the integral. And the area of the loop also, it is not as if the loop shrinks or the loop contracts. There is nothing happening to the area enclosed by the loop as well. So you've got B into A, but the only problem is that the angle between B vector and A vector, right? If it is north to south, you can see electric field lines going in like that. But as this plane keeps rotating, initially you would see that the planes, the plane would have a normal, right? So the normal to the plane, you will indicate it by an n cap direction. We will also be along that direction. As you keep tilting it by theta, what happens the moment you tilt it by theta, flux drops by a factor of cos theta, right? So the moment you tilt it by theta, because it was actually B dot A, right? In fact, it was B dot dA and you had to integrate the whole thing out, but that you could have written it as B dot dA into cos theta. And again, when you had integrated it, because this area didn't change, right? So you could have also written as BA cos theta, right? And especially when there is n coils, let us just say there are about n windings in the coil. So now the flux will be NBA cos theta will be the flux. But this theta, you can write it as omega t. Why? Because if at all you had a particle, right, moving along a circular path with a constant angular speed omega, and if this is theta, so you clearly you know that at any instant theta can be written as omega t, right? So therefore, this theta you could easily replace it with omega t, NBA. Let us call it cos omega t. So this will be your magnetic flux. Now, what will happen to this magnetic flux? So you see that as time changes, your magnetic flux also changes, because cos omega t, the minimum value is -1, maximum value is 1. So this keeps on changing, right? And clearly you can also observe this cos omega t fluctuates from -1 to +1 depending upon what is the value of omega t. So you clearly see that there is a changing magnetic flux. So whenever you see there is a changing magnetic flux, obviously you know that that gives rise to an induced EMF, right? That will give rise to an induced EMF. And how do you actually calculate that induced EMF? So you can say d phi b divided by dt, which is the rate of change of magnetic flux. Now you can just take a magnitude of this direction. You know how, it will be like from Lenz's law, it will try to oppose the change and so on. So I'm just writing the magnitude of this particular induced EMF. So what will turn out? Will turn out to be d by dt of, you just need to differentiate this whole thing, right? So let me write it in a different color. So let's just say you need to do a d by dt of NBA cos omega t, right? Now what happens? NBA, everything comes out. So d by dt of cos omega t, right? So it is something about minus sine omega t. If you just ignore all of the sign, you will get NBA some sine omega t. So you clearly, you see that you're getting a sinusoidal, you clearly see a sine kind of a induced EMF, right? So this is actually nothing but induced EMF. Okay, so you see a sinusoidal kind of an induced EMF. Now, what happens? Let us say if the potential itself, and these things are represented by a symbol like this, right? So this symbol says it's alternating between plus and minus. So you indicate, you put in a source, you take a power source, right, an active source, and then you plug it in there, and you plug one more resistor or something like that. Immediately you will see if this, whatever is a potential drop here, based on this potential drop, you can actually calculate the current. Potential drop divided by R. So along the direction of the drop, current will flow, right? That is something that you know for a resistor. So therefore, if at all you have a time varying potential, like this time varying EMF like this, so you see that that gives rise to a time varying current, and therefore you can have an alternating current. Now there is one more important question that I want to address here. That is the question of why do we specifically, in case if you observe the whole of your textbook, right, you would have seen that most of whatever you do, in fact, all of whatever you do, except for certain specific problems, be it deriving average and root mean square velocity, be it deriving a whole bunch of other things, you would have done it for sinusoidal alternating currents, right? Why do you think is the sine so special, right? Why do you think we need to work with only sine and cos? Right? Most of it is in terms of sine and cos. Aren't there any other alternating currents? No, certainly there are alternating currents. For example, you could have an EMF that varies like this, right? Till a particular time, this was, let's say, 5 volt. This is the power that is being supplied, and for some more time, it is minus 5 volt that is being supplied. Then later, it is 5 volt that is being supplied. So continuously, you can alternate, right? So there are EMF sources like this. But just think why you think that everything should be in terms of sine and cos. In fact, this is very, very fundamental to understanding a very interesting mathematical tool. However, I shall not be able to explain the tool in detail, but I'll be able to give you a quick overview of what I tend to say. Right? Have you ever asked yourself why is that we analyze only sinusoidal waveforms and then we claim as if we understand alternating currents? So give it a thought. Right? See, in fact, the actual reason why we do this is in later when you go to college and university, you will learn something called a Fourier series. Okay, so you will see that if at all you have a function, any function for that matter, you will be able to expand it in terms of Fourier series, and this Fourier series is an expansion in terms of sine and cosine. So you bring, like, let's say you take by the way, this is one of the most interesting things that I think you should know. Let me clear the screen once more. Right, so okay, Fourier series, right? So let us just say you have you have a graph like this, right? So let us just say you have a graph that moves along like this. It goes like this. So you will also be able to represent this graph in terms of Fourier series, or even if you have a graph like this, right, you'll be able to write this in terms of infinite sines and causes. You can actually expand it in terms of like sine and cos. For example, like in Taylor expansion, or like what other expansion you are familiar with. I think most of you might be familiar with Taylor expansion, binomial expansion kind of thing. So you expand out something in terms of other parameters, right? Similarly, Fourier, by using Fourier series, what you can do is if you have a function, you can expand it in terms of sine and cos, right? So this function, if it is f of x, I can write it to be sine of something plus sine of something else plus so on. I can expand it, or maybe I can expand it in combinations of sine and cos, or in purely sine or cos. It depends upon whether it's an odd function, even function. It depends on a whole bunch of other things. But the key idea here to understand is any arbitrary function, you can express it in terms of sine and cos, and that's a very, very beautiful work, and called the Fourier series and Fourier analysis. In fact, like you will use most of it when you come to engineering. So therefore, it turns out that if you understand how you need to work with sines and cosines, you have already understood how to deal with the small bits that make up this larger wave, right? So this is why we just study only specifically about sine kind of this thing. And luckily also you see that when you take a planar loop and then put it in a region of constant magnetic field, and if at all you just rotate it with constant angular speed, right? So you clearly see that naturally also you get a sinusoidal a field that's varying, an EMF that's varying sinusoidally. So I mean, generating wise, physically also, making up something that varies sinusoidally is quite easy. And second thing, if something is not a sinusoidal variation, you can study it in terms of sinusoidal variation. Very important thing that was established using Fourier series. Okay. All right, so this is one piece of interesting information that I wanted to share with you. Now, let us say you have a current. I'll quickly go over this average and root mean square, and maybe some significance of this average and root mean square. But one more interesting thing that I wanted to share today is, for example, usually in the textbooks we derive at average for sine omega t, right? But if at all you observe the potentials and currents given in like some of the problems, you might also have sine omega t plus phi, right? So if at all, like let's say current I is equal to I naught into sine omega t, right? And if current is also given as I is equal to I naught into sine omega t plus phi, we actually calculate average, right, and RMS for both only this function, and we make a claim that this addition of this phi does nothing much, and even if you have omega t plus phi, whatever was the RMS at this case, whatever was the average at this case, it will turn out to be the same thing here. This is also something it is slightly involved to show mathematically. Quite, I mean, it's okay to show, but it's easier to show graphically. So I will also show it to you. Why is that in textbooks we study I equal to I naught sine omega t, and we make an assumption that that same thing should work for I is equal to I naught sine omega t plus phi as well, right? But in general, how do we actually calculate the average current, right? For example, you have current as a function of time. This is current, and you have current as a function of time. So you've got current flowing, I mean, the variation of current with respect to time is like this. Now you want to find what is average current. Let us say you want to find what is average current. So what will you do? Average current is what? Total charge that flows through a particular cross section divided by the time interval in which those many charges cross through that particular cross section, right? So average current, you can clearly say to be delta Q upon delta T. Right? Now, how do you calculate delta Q? So you know that current is equal to charge by time, right? And in the instantaneous sense, you can also write it as dq upon dt, right? So that means if you want to know what is delta Q, what should you be doing? Ideally, you should be doing IDT integral. That will give you actually dq. You integrate on both sides. So you have delta Q is equal to integral IDT from T1 to T2. So that means what? From T1 to T2, if you're trying to calculate the average, right? So it's equivalent to saying integral IDT is nothing but an integral, or it's actually the area under this particular curve. So this average, you can write it as 1 by delta T times of integral T1 to T2 IDT. This is how you find the average for a current. But in general, if you observe, you have current here. So you're integrating that with respect to time, and then you're doing something like this. But in general, let us just say you have any function which varies with respect to time, right? Or with respect to some other variable x. Here my x-axis is time. So therefore, I'm talking everything with respect to time. Let us just say you have any function g of x. Okay. And you want to calculate the average of g of x in a certain time interval t1 to t2. Okay, so a convenient way of calculating this is actually average. We also write it in terms of this symbol. When you put it, enclose it in this bracket, so it means you're also talking about average. So you can say average of g of x, right, during this time interval, let us say t1 to t2, okay, will be nothing but you integrate this g of x, sorry, this should be time, right, because it varies with respect to time. So g of t dt integral from t1 to t2, the whole thing divided by t2 minus t1. So any function you've got, you know how to find out the average of that particular function. Okay, try to look at this. I'll be back in a minute. So this is g of t dt, right? So instead of let's say instead of current, you've given any function. So you can also say average of g of t will be nothing but integral g of t dt t1 to t2 divided by t2 minus t1. You can also visualize it. Why is this true? Because ideally, what is an average? Right, that means you're adding the whole thing. Like, suppose if I ask you what is your average score, right? So you'll take the mark scored in, for example, this is going to be a discrete summation, right? But nevertheless, let us say this is social studies, this is science, this is mathematics, this is biology, something like that. Okay, and you've got marks. So social studies, you've got this mark, science, you've got this mark, math, you've got this mark, biology, you've got this mark. So I'm just plotting your mark versus subject in one axis. So if I ask you what is the total score, then you are clearly going to say score obtained in science plus score in social studies plus score in math plus so on. You'll just add divided by total number of subjects, right? The same thing when it happens in a continuum, just that the summation is replaced by an integral. Logic wise, it is the same thing. You're taking an average of a function. Okay, just go through this. Just a second, I'll be back. Meanwhile, any doubts also, you can just put it in the chat. Okay, Sri Vasant, I'll let you know. A doubt. Sri Vasant has a doubt. I'll just let you know in a minute. Okay. Just a second. Take a look at this. I'll be back in a minute. Okay. Now there is an interesting question by Sri Vasant. Will the amplitude of AC current increase when we increase the angular velocity of the loop? Right? If yes, how? Okay. In the previous slide, when I was actually talking about generators and how do you actually generate AC current and so on, right? If you remember, I told you that you put this thing in a loop and you got like the magnetic flux to be. Let me delete this part. And okay, so you got the magnetic flux, which is nothing but phi b. You got it to be, if I remember, if my memory is correct, you got it to be NBA cos omega t, right? Now, what happens when you need to actually talk about the EMF? Now, the EMF generated will be d phi by dt, d phi b by dt, right? So, what will happen? NBA, and this is cos. If I'm only taking a magnitude, it will become sine omega t. You have an omega also here. When you differentiate cos omega t, you have got one omega also outside. So you got omega NBA sine omega t. So that means what? You kind of rotate it with more and more angular speed or angular velocity. Now what happens is you see that your induced EMF also increases. Now that is true because you have to spend more work in doing so, right? You are spending more energy when you need to rotate it like really faster, more energy per unit time kind of a this thing. So therefore, the induced EMF will also be slightly more, in fact, quite a bit more, and it turns out as a factor of omega. Whatever will be the omega n times BA sine omega t, right? So that happens when you go faster, right? Now this is the average. Let me show you in the next graph. If you observe this, I have plotted sine 2t, right? So because like I cannot plot a variable, I just took, so you can consider it to be like sine omega t, where the value of omega is 2. You can consider like that. So this is a graph of sine omega t, right? Now, if I need to calculate the average of this, remember what you need to be doing. So average of, right? If you need to be calculating average of sine omega t over a whole time period, then what should you be doing? You're going to integrate sine omega t with respect to dt for one complete time period, right? So let us just say the time starts here. This is one complete cycle. So for this one complete cycle, you're going to integrate this throughout, right? So what are you going to do? Integral from 0 to t, right? One complete time period, and you've got sine of omega t dt divided by, if this is 0 and this is t, you've got t minus 0. So this is how you find the average. And clearly, if you observe integral 0 to t, this is f of x, right? F of t. So this f of t dt. So this is nothing but integral 0 to t f of t dt divided by t, capital T, which is t2 minus, which is t2 minus t1, which is nothing but capital T here, t minus 0, right? So clearly f of t dt is nothing but what? Area under the curve. So area under the curve, you've got this area, which is nothing but positive, this area, which is nothing but negative. So effectively, you see that average, if you average this out, you will see that the average will turn out to be 0. Why? Because the numerator turns out to be 0. Okay, so if at all you are given a sinusoidal current, which is, let us say, I is equal to I naught sine omega t. So you clearly know that the average value of this current over one complete time period or one complete cycle, it is going to be 0. I average over one complete cycle is going to be 0. If you want to visualize it in terms of charges, if this number of charges are moving through one particular cross section left to right, the same number of charges in the same time will move through the cross section from right to left. So effectively, if you look at it, over one time period, over one complete cycle, it look as if no net flow of charges has actually taken place. Now this is something that you can also derive. I have shown it to you graphically, but you can also take an integral and then really perform that integral, get it in terms of cos, substitute the limits, and you will see that I average will anyway turn out to be 0, because this is a fundamental reason. Now I told you one more question. I asked you a question. I equal to I naught sine omega t. If the average of this turns out to be 0, how do you actually guarantee the average of omega t plus phi turns out to be 0. So this you can treat it to be a function like sine of omega t plus phi, where the value of omega is nothing but 2 and the value of phi is nothing but pi by 4. If you observe carefully here, what happens? The amplitude does not change, time period does not change. All that it changes is there is some shift in the along, let us just say, along the x-axis, right? The graph which was supposed to be here, it has just been shifted back by a certain amount, which is this particular amount. Except for that, everything else is the same. Now here also, I'm going to calculate the average, right? If I'm going to calculate the average, what would happen? So I'll take from here for this green part. My average will start from here because this is where the cycle starts. This is where the cycle ends. So over this whole time period, this area and this area will also add out to be 0. Additionally, this area and this area is also equal to this red shaded part area, right? So it is just, if you are adding, sine of 2t plus phi, sine of omega t plus phi, if you add that phi factor, all that you're doing is you are shifting the graph left right. That is not changing the amplitude, that is not changing the area under the curve, that is not changing the time period. Then why will the average change? Therefore, the average also does not change. So therefore, in all of the analysis that you do in your textbook, if you calculate average for sine omega t, same as the average for, average as in, like, if at all you have a sinusoidally varying function I equal to I naught sine omega t, whatever you get as the average, in this case, average over one complete cycle is equal to 0. Here also you will see that average over one complete cycle will also be equal to 0, even for sine of omega t plus phi. Okay. And by now you should have also understood that for in the case of an AC, if at all you have sinusoidally varying current, right, or sinusoidally varying potential, anything. So let me write for both. If at all you have some I that is varying sinusoidally as I equal to I naught sine omega t, right? So here also it turns out this I average is actually equal to 0. If at all you have, instead of this, you have got it to be in terms of, let's just say, potential. So EMF. So this is equal to E naught sine omega t. Here also you will have that E average, which is equal to 0 over one complete cycle. All of this is averaged over one complete cycle. Okay. Similarly, we will also see that if at all you prove root mean square, root mean square value, right? That will also be the same for both sine of omega t and sine of omega t plus phi. So this also I would want to show it in the. Just take a look at it for a few seconds and I move further. We'll solve after this. We'll solve a bunch of problems. It's going to be 7:40. Okay. Now let me move on. Next slide. Here I've just done nothing. If at all you want a root mean square value, RMS value, right? RMS value. What do you do for an RMS value? So you first take, square that particular value, right? And then you take the mean of such a thing, right? So you're actually squaring this and you're taking a mean of this function. So if you take an average like this, so average of sine square omega t. So this will give you the RMS value, right? So if I equals to I naught sine omega t, so you know that I RMS will be equal to what? I naught by root 2, right? I'm not kind of deriving this, but I'm just making the statement this IRMS is equal to I naught by root 2. But if you want to derive, that is going to be straightforward. So if at all this is IAC, right, square on both sides, so you get sine square omega t. So you can write it as, in terms of cos 2 theta, right? 1 minus cos 2 theta by 2, 1 plus cos 2 theta by 2. You can write it in terms of cos 2 thetas, and then you can integrate the whole thing out, substitute the appropriate limits. It's an unnecessary calculation during a class. But nevertheless, if you do this, it will turn out that IRMS will be equal to I naught by root 2. Now, the only thing that I want to show it to you here, which is not shown in your textbook, is the fact that if you have I naught by root 2 as the RMS for sine omega t, right? So what will be the RMS for Sin omega t plus phi. Again, the same thing will be the RMS. Why? Here also you see that if at all you're calculating IRMS, what are you doing? You're just taking average of mean of this because you've already squared and you're taking mean of this, right? So that means how will you integrate? You'll integrate it from 0 to t, one complete time period, one complete cycle, and you'll also integrate it as sine square 2t dt integral divided by one complete time period. This is an integral that you'll perform. Similarly, for this you'll perform, you'll average this out and you'll perform the same integral. But here also you see that this adding this phi does nothing, but it just shifts the graph left, right? And therefore, whatever was the IRMS there for sine omega t, same thing will be the RMS for sine omega t plus phi. Right. So this is one more interesting aspect that I wanted to show it to you. But IRMS, you know how to calculate it. I not by root 2. Just have a quick look at this derivation, but okay. Now I want you to try the first, uh, quiz question. Ideally, it's not first quiz question. It is first quiz question in AC. Right. So try to calculate this. The RMS value of potential difference V is shown in the figure. This again had appeared in NEET 2011. So try to calculate this and tell me what do you think will be the potential difference V that is shown in the figure. Anantanarayan, correct. This will be NBA omega sine omega t, correct. Oh, some of you have asked a break long back. Okay, after this problem, I'll give you a quick break. Right? Try to solve this problem. It's just an average this thing. So Atharva, obviously, so it will be useful for CBSE because if it's a board kind of a pattern where you have to write explicitly things down, most of the time the derivation that is given in your NCRT textbook will be treated as the proper derivation. But when it comes to MCQs, right, you can use as many shortcuts as you see. In fact, I would say it is more or less like writing a pre-NEET or pre-JEE, right? Just that the level is going to be slightly simpler. That's all. Okay, and focus on some traditional concepts like, see, for example, this meter bridge, potentiometer. So such kind of things, just go through, spend some little more time. And assertion reasoning questions, be really careful. Do not try to hurry up and mess this up. And also, whenever a reading comprehension is given, when a case study based question is given and a passage is given, please do read the paragraph. Do not assume that no, I have not read the paragraph. Only by directly reading the question I've got the answer. Don't do that. There could be something written in the paragraph that might be important. So please do read the paragraph. If it looks familiar, at least read it fast, but read the paragraph when it comes to case study based questions. And when it comes to assertion reasoning, be really careful while you answer, right? Exactly, Ananta. I agree with you on that completely. Right. So, in fact, I was looking at some previous year CBSE questions, but it's not there in the MCQ type, right? So the long answers turns out to be really calculation intensive. That's why I just thought I would not want to put it up, and I would go ahead with previous year NEET questions. Calculations are extremely lengthy. I completely agree. But at least you've got one relief that you need not give the exact value, right? So okay, solve this problem, and after this we can take a quick break. Believe? Yeah. Come on, already. I think this should be easy. It should not be taking a lot of time. I think it's been sent as a poll. Okay, it's 50% of the class feels it is option B. Let's quickly check this out. But why others? See, it's simple, right? You've got the RMS value. Again, do not search for the formula. You're just given some graph. What is RMS value? First, for that, first square this thing up. So this V naught will become what? V naught square. It will be like this, right? It will go on till T by 2. And till T it is actually 0. Again, it will go on V naught square. Again, it will drop down to 0 and so on, right? So now what happens? You're just calculating root mean square. Okay, so first take mean of the square, then take a root of it. So this is square, you're squaring this, take a mean of the square. Okay, how will you do that? If you're taking a mean, that means you're averaging this out, right? So what is this function? This is function v versus t, right? But now you're trying to find out mean square. Now this function is nothing but v of t the whole square, right? This is v of t the whole square. You're trying to take a mean. You're trying to take a mean of this. That means again it's actually the area under this curve in one complete time cycle, which is starting from 0 to t. So in this complete one time period, what is the area enclosed by this curve? Clearly it is v naught square into t by 2, right? So clearly it is v naught square into t by 2. And then what are you actually doing? Divided by, right? You're taking the mean, right? So you're also dividing it, take a square root, and you're also dividing it by t by 2. Okay, just a second. You're taking a mean. So mean will be like this, right? So mean will be, and this is actually the integral value of this square. This whole thing is the mean. You're taking one more square root. So what will you get? V naught square t divided by 2t gets cancelled. So V naught by root 2 is the answer. Simple stuff. So the answer is V naught by root 2. This came in NEET 2011. Exactly, I think it's a 30-40 second problem. Right? So if you understand, see, that is why I keep insisting that don't just vaguely remember the formula. RMS is, I naught by root 2 or something. It might not be useful in certain areas. On the other hand, even if you forget that I naught by root 2, at least somehow you can manage and derive. But understanding the fundamentals is going to be important. So RMS means what? You're actually squaring, right? You're taking a root, so maybe you should understand it this way. If in case if you forget what is going to be the right definition of RMS, so look at this. You're taking a root of what? Root of mean. Mean of what? Mean of the square. So you're taking a root mean square, right? So once this meaning is clear, I think it should be straightforward to solve this. Okay. Now let us look at the resistor, capacitor, and the inductor's response to AC. Right? So how does a resistor, how does a capacitor and inductor respond to AC? For example, in general, let us just say you have some potential drop, you had a resistor, you had a potential drop. If this is the direction in which current is flowing, so you clearly know that along the direction of the flow of current, the potential drop is nothing but IR. Now you might have a capacitor, you might also have an inductor. So in the case of an inductor, if current I is flowing like this, right? So this is the potential drop, right? So let us call it VAB. VAB is equal to IR. This is potential drop along the direction of current. Similarly, here also let's call it A and B. So if this is I, that means positive charge will be on this plate. So the potential drop will be how much? Q upon C, right? And this you can also write it as 1 by C into, how can you write Q? You can write it as IDT integral, because IDT integral actually gives you the charge, right? Similarly, for an inductor, what can you say? You can say that VAB is equal to L times dI by dt, right? So you see that here there is a differential that's been involved, here there is an integral that's involved, and here the proportion is VAB is equal to IR. Now in this, I want you to notice one very, very important idea. Let us just say at time t equals to 0. At time t equals to 0, what happens if at all I say VAB, right? If at all I say VAB is equal to let us just say 2 volts, okay, then immediately at time t is equal to 0, exactly at this time t is equal to 0, a current will be established, and the current will be nothing but what? VAB upon R, right? But whereas when you come to an inductor, In this case, at t is equal to 0, if at all VAB was equal to some finite value, let us just say it is like 5 volts or something, right? Normal DC stuff. You cannot say that at t equal to 0, there will be a instantaneous current that will be set up, right? Because the problem will be that if at all you say that at t is equal to 0, there is some finite current, maybe let's just say you say it is zero point 0.2 amperes or something, it's a problem because 0 to zero point 0.2 ampere, the current has changed instantaneously in 0 time interval. That means what? This dA by dt, it will be a very, very huge number. What will be the rate of change? 0 to 0 point 0.2 ampere in an instant, in 0 time. That means dA by dt will turn out to be infinity. So that means what? You cannot have instantaneous response, right? The characteristic of an inductor, it turns out in such a way that you cannot have an instantaneous response, instantaneous current, or you cannot have a current that has been set up in the instant you close the switch, right? Connected to a potential drop and you close the switch, you cannot have instantaneous change in currents. Okay, this is one important idea I want you to understand for resistors and inductors, first part. And second part, you also know how all of this would actually behave, right? So you know that it has a capacitor, has a capacitive reactance, and this inductor has a, again, it has a reactance, right? And for R it is only R. For capacitance you have some capacitive reactance. This also you can call it inductive reactance. Okay, and you know that in the case of a inductor, what will happen? Always it's better to talk about current leading or lagging something behind. Now I want you to comment, let us just say current, but ideally this leading lagging is not very precise. It's not as if the inductor already knows what is going to come up front, or it is not as if the inductor knows later or something. Just that when things happen after, it's a cyclic process, right? So it happens in the second cycle or third cycle, it looks as if this inductor is lagging behind, or it is like running ahead, right? So it's exactly not, because sometimes there is another question. If at all you say that current is lagging behind, right? Or current is leading. Current is lagging behind, understandable. Current is leading, there is a problem, right? Before even you supply a potential, current is leading, means from where has that current come? So it is not as if the current is leading in that sense. It's a cyclic process. If you observe continuously through the whole cycle, so if it is leading or lagging, it is with respect to the older one, right? So the potential at this moment, if you know, right, the inductor is still responding to what happened sometime back, right? And if I say something is leading, that means what? It has completed one cycle. In the second cycle, it is leading, right? So it is something that I want you to understand as well. I want you to quickly try and answer this particular problem. This will help you understand what is this reactance and this thing for capacitors and inductors. Come on, make it fast. I think we've got a little less time. Try to solve this quickly. A promised a break, is it? How many of you need a break? Quickly, just let me know in the poll. Please send a quick poll on whether people need a break. Someone respond in the chat. Please have a quick poll on whether people need a break. I'll think about giving a break. Okay, fine. Just take a break. I think like taking by the time you answer a poll, you can take a break. Take a quick. So it's 7:57. Take a quick 5-minute break. Maybe we can start at around 8:02. Okay, 8:02 or 8:03. The class will resume at 8:03. Maybe you can come back and answer. That's okay. Class resumes at 8:03 p.m. But please come back because I've got a bunch of problems to finish. So take a quick break and be back. Shall we resume, guys? I think it's time. Hope all of you are back. Right? My pen. Right. Let's quickly look at this. This problem also I put in so that we can revise a whole bunch of formulae and things like that. Now you know 2 to 3 things. One, RMS how to calculate, average how to calculate for any sinusoid, any sine or any cos. You know how to calculate, and that too, after you calculate that, you again know that if you calculate it, like let's say for I equal to I naught sine omega t, you know that is the same as that you will get it for I equal to I naught sine omega t plus phi. Having this additional phase factor does nothing much to actually RMS and average, so this is something that we explored using the idea of graphs. Okay, this is one complicated idea that we explored using the graph part. Right now what happens is, already we are used to doing v is equal to ir kind of a thing, right, for a resistor. So similarly for all other components also we try to do something like v is equal to I into some kind of an r. This is not exactly resistance, right? That is where the idea of reactance would come in. For example, for capacitor, what happens is it's easier to find, right? This is in fact not hard. I'll show you. I'll not do the exact derivation, but I'll show you how it is done. For example, you've got a capacitor like this, right, connected to a EMF source E. Now what equation will you write? So from here to here, so you know that there is a potential drop E, and clearly current will just get deposited. This current will deposit positive charges here. So this side there is a potential drop Q by C. So you know that this E should equal to Q by C, right? And this E is, if at all this is a sinusoid, right? If at all it's a sine kind of a function, so you can write it as E naught sine omega t. That has to be equal to Q. You can write it as what? Integral, right? You can write it as integral I dt, right? 1 by C. So if you observe this, if you kind of evaluate this thing, right? So you've got epsilon sine omega t is equal to 1 by C and integral dt, right? This is what you've got. Integral I dt is what you've got, right? So if you kind of solve this, again, you will know that you will get the answer, that is I. It will turn out to be a sinusoid, right? Now this I, it turns out for a capacitor, this current, right, it actually leads potential. So for example, if at all the potential drop was V is equal to, let us just say, V naught sine omega t, then, right, then the current I in the capacitor will be I naught, right? It will be I naught. Instead of sine omega t, you will have sine omega t plus pi by 2, because current in the capacitor actually leads voltage. Similarly, for an inductor, if you have, you can also say I naught into sine of omega t minus pi by 2. Inductor lags by pi by 2. Now, if you need to calculate what is this I naught in both the cases, so you can just see clearly in this case, this I naught will be nothing but V naught upon 1 by omega c, right? This 1 by omega c acts like a value of, the how is resistance to a resistor in an AC. Similarly, 1 by omega c is like a resistance in the case of a capacitor, right? So this is called capacitive reactance. So you've got 1 by omega c. Here you will get it to be V naught divided by omega L for in the case of an inductor. So in general, you can say if I have any elements RCL or any combinations of RC and L, by the way, you only have series RCL in the syllabus, right? So if you have it in series, so you can just say that, I'll take V naught divided by X, right? If it's for a capacitor, I'll take XC. If it's for an inductor, I'll take XL. If it's for a resistor, I'll take XR. XR is clearly nothing but R. All of this, This is how you calculate peak, right? The moment you calculate peak, calculating RMS should not be hard, right? So just calculate this first part. calculate it and quickly give your answers. Okay, I'll give you a quick 1 minute time. Let's just say take 2 minutes and then solve this out. Divya, none of the options are matching. That is surprising. I think it should match. Let's quickly see. Others, meanwhile, please respond. Yeah, looking at the responses, it looks as if most of you have given the right answer. Divya, just check your calculation once more. Right, since most of you have answered, let me quickly go ahead and calculate. So what do you get here? Right. So a 40 microfarad capacitor is connected to a 200 volt 50 hertz AC supply. It is given in hertz, but you need omega t, right? So for example, so you can clearly do, this is a case of a capacitor, right? So you can say V naught divided by 1 by omega c. But this omega is not 50, by the way. This frequency is 50, right? So 2 pi f is equal to omega. So 2 pi into 50, it's equal to omega. 100 pi is equal to omega, right? So V naught is what? V naught is nothing but 200 divided by 1 divided by omega c. What is omega c? 100 pi into 40 microfarad. So what do you get? 200 into 40. Uh, Let me erase this. What? Yeah, what calculation do you get? This is a simple calculation, I believe. 200 into 40 into 10 power minus 6 into 100 pi, roughly, right? So you've got 1, 2, 3, 4, 5 cancel. This is about 8.8 into pi, right? So what answer do you get? 1 by omega c. Correct. So this will be nothing but your peak, right? So what is this? By the way, don't confuse it. This is not your actual, RMS. This is only your I naught, right? I naught divided by root 2 will be your RMS, right? Let's just take quickly calculate. So what do you get? I think it should be roughly about zero point 0.8 into pi divided by root 2. Hope it should be 2.5, right? So this is going to be zero point 0.8. Since some of you have told this is not matching, so I just thought I'll just quickly check. Divided by 4. Just a second. So you've got a V naught and this thing. RMS value of the current. Right? You've got I naught here. Yeah, I think it's a problem. Let me quickly check. Exactly. Sorry, yeah, this 200 is the RMS part. Correct. So thanks. By the way, I was also wondering. So this is connected to a 200 volt. So in general, this would mean this is the RMS, this thing, right? So you are given, so to calculate V naught, right? So V RMS is nothing but V naught by root 2, right? So that root 2 cancels with this root 2, leaving behind 0.8 into pi, which turns out to be roughly about 2.5 amperes. This is the right answer. Correct. That is the RMS value. Good. In general, when you say it's a 200 volt source, that's the RMS value. Right? So I've got one more interesting question. Just solve this. I think it should be interesting. Think and answer this question. Take some time, take 2 or 3 minutes to analyze this, think and answer. By the way, in fact, I see some of you asking in the chat, isn't just a second, isn't it like IRMS is equal to VRMS by like X whatever, XC or XL? This is also true, right? I'm not saying something that's new. See, I just told I peak is V naught by XC, right? But you know IRMS and the relation between IRMS and I peak. You already know the relation, right? So it has to be IRMS has to be I naught by root 2. So if I just divide both sides by root 2, so let us just say I have this. Just a second, I'll go back to this next question in a minute. Okay. So let us just take this blue color. I naught is equal to V naught divided by XC, right? So divide both sides by root 2, V naught by root 2 XC, right? So I naught by root 2 will be what? IRMS. V naught by root 2 will be what? VRMS divided by XC. So this equation and this equation means the same thing. Okay, you can do it the way you like. Right? So if at all you are doing it directly in terms of VRMS, then you will directly get IRMS. Right? Okay. So hopefully this part is clear. Now try this out. Exactly, Dhruv. VRMS is equal to 200. Correct. Just look at it once more. You should be able to get it. By the way, please answer this question. Second question. Poll. Okay. See this question. This question, right? Majority of you have pointed out that this is not majority, right? I think 40% of you feel it is option D. Option A, roughly 26%, option B, 26%, and option C, 9%. Okay, I'll tell you why people think it is option A, right? Option C, many of you have not pointed out, so I'm happy, right? So but option A and option B, people point out usually because we see that current is given, voltage is asked. So you know that for an inductor, right? So you know that current will lag the voltage. So using that logic, some of you might have tried and tried to get this. but remember, whenever you are given inductor, you are given the potential difference or voltage across the inductor, right? So this EMF or E or the potential is going to be what? LDI by dt, right? So that means what? You want to calculate EMF, you should not look at current, rather you should look at di by dt. It does not mean, whenever people say inductor lags, inductor current lags behind, or whenever say that capacitor current is ahead, in such kind of cases, it does not mean that the waveform's shape should not change. There is no such requirement like that. See, this is EMF E and this is LDI by dt. So your observation should be on di by dt, right? So di by dt is what? It's a straight line till 0 to t by 2, right? Di by dt is what? Slope of the slope of the tangent at that particular point. So now for a straight line, every single point, you take it at any point from 0 to t by 2, you take any point and draw a tangent and calculate slope of the tangent, you will get the same value, which is nothing but slope of this line. That's a constant. So therefore what? 0 to t by 2, you should have a constant value. If you observe, this is the only graph that has a constant value from 0 to t by 2. Similarly, at t by 2, right, there is, at this particular point, this function is not differentiable. Why is it not differentiable? Because left hand limit will tell this, right hand limit will tell this. Left hand limit gives one value for the slope of the tangent, right hand, if you approach it from the right hand side, that will give you one more value for the slope of the tangent. So therefore the point is not differentiable at that point, right? Am I correct? From differentiability, continuity, right? So you know that this is not differentiable, leave that. Now in this particular point, you know that again slope has to be constant, but slope has to be what? Negative. Constant slope, negative. So therefore option D is the right answer to this question. Okay, this had also appeared in NEET. I think this is fairly recent. I don't exactly remember the year, right? But such kind of questions, you should be happy if such kind of questions come up, because requires very less calculation but little bit of conceptual understanding, right? Do not go by the logic. Whenever a wave, I kind of have a feeling something like that might come up. Whenever a waveform for I is given, whenever a waveform for V is asked, do not go blindly by the logic that current lags or voltage lags or leads. Okay, so see, it kind of works with the sinusoid with the phase difference. Why? Because this sine, when you differentiate, you get cos, you differentiate again, you get back sine with a little bit plus minus sign difference, right? So you can manage it with that extra phase, but for such a function, for such a curve, it need not be the case, right? So just be a little careful with such kind of questions. Hope all of you are clear with this part. So option D is the right answer to this problem, right? People who have answered A, B, be slightly careful. And people who have rejected C, just because of the fact that the function cannot change shape, right? It has to be like this. It has to be something like a sawtooth kind of this thing. That's also an incorrect logic for skipping up C. So be slightly careful and solve that. Okay. Now try to do this problem. In an AC circuit with voltage V and current I, the power dissipated in the circuit, right? If you remember, the power dissipated in the AC circuit is what? Vrms, Irms, cos phi. That is the power factor, right? Looks like I've already given half the answer, but anyways, just check and let me know what will be the answer to this question. Let me quickly erase this. Okay. Ananta, some doubt. Okay. But where is your doubt, Ananta? Can someone post Anantaragwan's doubt in the stream chat? Okay, I'll come back to that. So please finish this up. This is, I think, a straightforward question. So poll result, right? So most of you have said it is option A. Option A is the right answer. I accidentally realized I had given the answer already, right? Some of you, I don't know why people have given different answers, right? All three are incorrect. It clearly depends on the phase relationship between V and I, right? Because if you remember, power dissipated, the formula was Vrms Irms into cos phi. So whereas this phi is the phase between V and I. So clearly the power is actually dependent upon the phase between V and I. Remember, do not get yourself confused with this. Okay, try another problem. Some of you had asked, I mean, if it's a capacitor, what you should be doing, right? So this is again very, very simple. So I'll just give 2 minutes for you to finish this. Looking at the options, it feels as if, yeah, the calculation, I don't think it's complicated. So something might cancel out in a nice way. So make it fast. Try to calculate this. 2 minutes. Acha, Ananta's question. A wire can be thought of as a solenoid with infinite turnings and infinitesimally small area. Okay, and self and L. Okay, self inductance is proportional to n square and a. So when we apply Faraday's law in an LC circuit, okay, why do we ignore L dA by dt of the wire? The product of n square and a may be finite. No, I have a problem itself with treating the wire, treating the wire as a solenoid with infinite turnings and infinitesimally small area. Because see, fundamentally, let's say you take a coil and then you connect it across an EMF source, right? So if at all it's current flowing through the coil, so with respect to the EMF that is set up, so you can clearly see that there is a current flows through in circular loops kind of a this thing. Therefore, there is some LDA by dt associated with it. But a wire, why do you want to actually think of it as as a solenoid? I have a problem in treating the wire with a solenoid itself. I think that's not quite a good. I think that's need not be done that way. As to think of wire as a solenoid itself is a problem, because in a sense you're trying to say that clearly if you establish a potential drop, in a wire, it's just going to a steady current is going to be established, right? See, in fact, there are going to be not only this, there are going to be multiple problems associated with this. I'll tell you one more logic. Think about this, Ananta. Let us just say you have a wire, normal wire, you connect it to a normal DC battery, right? After initially there could be some problem, because every single circuit has an associated inductance, associated capacitance and everything. But ideally, after some finite time, what happens? A steady current is established, right? So because of that straight wire at any finite distance, right, so you don't see a varying magnetic field, right? Observation wise, you don't see a varying magnetic field, because it's a steady current that's been generated in the circuit. So you do not have some induced you do not have something like a varying magnetic field generated or something. A steady current carrying coil generates a steady magnetic field at some finite distance, right? But treating it of a solenoid is also a problem in that sense. So I think fundamentally, to think of it as a solenoid, I do have a problem, but I'll think about it. I'll think about it a bit more and see. But I don't understand why you should think of it like that. But treating it as a solenoid, see, you're trying to say that the current goes around in loops. I have a problem with that, right? So right? Ananta, I'll come back to this question once more. Let me think about it a bit more as to why you ignore it. But I think I mean, as much as I think at this moment in time, so I feel it that the assumption, uh, the way you treat a wire as a solenoid itself seems a little problematic for me, right? So I'll also try to look if there will be any other problems that will be associated with this. I think the assumption itself might not be a good one. Uh, but do we approximate it like that anywhere? I don't think so. We do. Anyways, coming back to this question, in an AC circuit, alternating voltage something is given connected to a capacitor of capacity 1 microfarad. The RMS value of the current in the circuit. So clearly, you can see IRMS is VRMS divided by omega L. Right? Straightforward. There is nothing complicated in this. So here it's only this that is given. 200 root 2 is actually E naught, right? But you want VRMS, it has to be by root 2. So you will get only a 200 out here divided by omega. What is omega? Omega t, right? So you've got 100 into, you've also got 1 microfarad, right? 1 into 10 power minus 6. So you've got 200. So which is like, let's just say 2 into, this is micro, right? Have I made a mistake? Just a second. So microfarad. Yeah. So 20 milliamperes is okay, but why is it even milli? There is a problem. Looks like there is a problem, right? So 200. Yeah, but why is it alternating voltage is connected to a capacitor of capacity 1 microfarad? Can someone let me know if I'm missing something? Probably my brain has stopped working, maybe. So just a second. Sorry, it's a capacitive circuit and not an inductive. It's not an inductor. Thank God. I was just wondering, otherwise it will become mega amperes, right? Glad that someone pointed it out. So it is 1 by, I'm still thinking about some questions. So, right. So 200 divided by 1 by 100 into 10 power minus 6. Right. So overall it is 20 milliamperes. Good. So 20 milliamperes is the right answer to this question. How much time do we have? I think we are already extending beyond time. Okay, I'll do something. I'll send these questions. I do have maybe, no, I think if I go back, you might be able to see the answers. So I think I have about 4 or 5 questions like that. Maybe we'll discuss it next time whenever we do AC, right? So with this, let's end today's class. Right, I want all of you to actually go back and revise all of this. So I'm just keeping these CPSE sessions quite simple relative to what we usually do for KVPY and JE, because I do not want to trouble you at very close to your board exams, right? But nevertheless, these are I deliberately chose some neat questions because I just thought it would be a good revision. So I would also suggest you to look at some previous year neat questions if at all time permits. Right, my kind of feeling is if you look at neat questions before, let's say, 2000s, there are like quite a bit of simpler questions and high chances that such questions could end up being in your CPSE paper. And there are a few simple questions from 2000 to 2020 as well, right? Try to go over those neat questions as well, right? If not JEE, I think neat questions, a quick overview of them might help. So please do that. I've got like a couple of other announcements as Madhumam pointed out. Next week and the next week after, that is 13th December and 20th December, we do not have a class. We have a break because of board exams. So all the very best for your board exams. Do check out the app as well. I think some of the tests are being added. I just got a message that some tests are being added. I've also asked people to add some more tests. So that should also be added. So this next few days, you can continuously keep checking the app as well, right? So that few more tests will also pop up. Hopefully today's session, I believe some of you might have found it to be useful, right? So anything else? Yeah, when it comes to your board exam part, right? So just if you have got like 2 or 3 days, I think you've got 2 or 3 days, so 3 to 3 days, right? 10th is your physics exam, am I right? So one day I would suggest you revise only your electrostatics part, which is like electric charges and fields, electric potential, potential energy, and that capacitance part, along with current electricity. Right. So spend, because current electricity, by the way, most of you are really good. We have done in detail KVL, KCL. We have, I think, we have done it to a quite good extent. So, but what we have not done probably is during the class. I remember not doing problems in that drift velocity and other things like that, right? So resistivities are given and do some small bit of calculation. So just look at that, and so spend one complete day for all of this complete electricity part. Magnetism and matter, spend one day, and for AC alone try to spend one whole day is what ideally I would suggest, right? Because AC, I'm expecting it's easier to ask tiny little problems, and there is some scope for if you try to quickly solve, you might miss a root 2 factor. See, when I tried to make, I was about to make a mistake. Instead of writing a micro, I might have got a mega, right? This is okay because there is an opportunity to correct, but ideally in an exam that will be a problem. So do spend some time. I would ideally say spend some time on AC, right? And so wind it up like that, and be confident whatever you have learned should be quite good as far as board exam is concerned. There should not be anything new or anything complicated that should pop up, and do not burden yourself by learning anything new. Right, if at all you want to learn anything new, finish it up at least today and tomorrow. Do not extend it beyond that, right? At least the day before the exam, do not read or study anything new. Whatever you have done so far, revise. If at all you have time, you can also go through NCRT exemplar problems. Okay, few questions in NCRT exemplar will be hard, but there will be simpler questions as well in NCRT exemplar. But you can, NCRT exemplar, some of you might have as a hard copy, otherwise it's available online, right? Please do check out NCRT exemplar as well. At least those theory kind of questions you can go through NCRT exemplar. And when you're revising, I would suggest you to go through solved examples. At least if you don't have time to work out everything, at least you read some small section, do a bit of solved examples, whatever comes in text. And I think you should all come out with flying colors in your examination. You have all done a decent amount of preparation, really good preparation so far. So it is only the confidence that matters. And I mean, if it's a descriptive paper, I might be a little concerned, but if it's an objective paper, you have been writing so many consolidated tests, you have been writing weekly tests every single week, week after week. So I think you should all be used to writing an MCQ exam now. So all the very best for your board exams. And I would like to hear that all of you did really well, extraordinarily well in your board exams. Do let me know, let your mentors know after your exam. I would be extremely happy to hear that your exams went on well. Okay, Ananta, but still I'm not convinced with the answer that I gave you for that question. I'll have to think about it some more. Maybe next time when we catch up, I'll try to answer that. I'll also see if there are any other problems associated with this. And after this, we will also see, next time when we meet up, hopefully it will be for NEET and JE, we will do some challenging problems. Till then, bye-bye. All the very best, guys, for your board exam. Okay, and regarding the task, Madhu ma'am wanted me to just inform one more thing. Your regular task will start from 20th December, which is Monday, right? So meanwhile, if some of you are interested, you think board exams, you're not going to anyways prepare much, or ideally you should not think that way. Do prepare, take it up seriously, right? But if you think that you have done adequate amount of preparation, then please do look at your advanced lessons based on your same board syllabus, which is L37 electrostatic combo problems, L38 resistor circuit techniques, L39 miscellaneous resistor circuits, and L40 miscellaneous capacitance. All of these are fairly advanced lessons, so do take a look at it if you find time. And again, do not start all of these lessons right before your physics exam. After your physics exam, if you find time and if you're well prepared for other subjects in boards, please do go through. Right? Okay, bye bye, guys. Take care.